You look into a mirror. Light hits glass. Light bounces back. You see your face. It feels obvious. It feels like a simple story. Light arrives, reflects, done. Except that story is not what the mathematics says is happening, because when light goes from here to there, it does not take one path. It takes every path, not one after another, not as a metaphor, all at once, every possible route the photon could take, every possible history connecting the start to the end. Now take the simplest example, a clean piece of glass. You shine light at it, and roughly 4% reflects while 96% goes through. That sounds like a neat division, but here is the question that ruins the neatness. Which 4%? How does an individual photon decide whether it reflects or transmits? It doesn't decide, that's the point. In the path picture, a photon does both. It reflects off the front surface, it goes through. It reflects off the back surface and then back out. It ricochets internally. It takes ridiculous detours. It explores an absurd number of possibilities. And each possible path carries something we call an amplitude. Think of it like a tiny arrow. The arrow has a length and a direction. The length is related to how strongly that path contributes. The direction is related to how long that path takes, because time makes the arrow rotate. To predict what you actually observe, you do one thing. You add the arrows, all of them. The straight paths, the curved paths, the ones that bounce once, twice, 1,000 times, the ones that drift far away and come back, the ones that seem too crazy to matter. And here is the miracle. Most of the crazy paths cancel out. Why? Because their arrows point in all sorts of directions. Add a bunch of arrows pointing everywhere and they erase one another. They don't build a result. They wash out. But paths that are close to each other, paths that take almost the same time, produce arrows that point almost the same way. Those arrows reinforce. They add. So the straight line wins, not because the photon chose it, but because everything else self-destructed in the sum. The photon didn't pick one history. The universe added all histories and the cancellation selected what survives. That's what a mirror really is in this language. Not a surface that forces light to choose reflection, but a place where the arithmetic of all possible paths produces a strong reflected outcome. And if you take that seriously, the mirror stops being a simple object. It becomes evidence that reality is doing a computation you never asked for. Now comes the part that makes this hard to dismiss as just math. If those crazy paths were truly nothing, if they were only a bookkeeping trick, then removing them should change nothing. But it does. Block a path you shouldn't need to block, and the final answer shifts. The pattern changes. The result changes. Which means something in the system was, in some sense, exploring that option, because removing it alters the sum. This is why diffraction and interference aren't decorative side effects. They are the fingerprints of the path-summing rule. Take a mirror edge. Common sense says the edges are irrelevant. Light hits the middle, it reflects. Angle in equals angle out. The far edge should have nothing to do with your reflection, except it does. Because in the path picture, some paths bounce off the edges. Most of their arrows cancel because the timing varies wildly. So you normally don't see the contribution, but now do something surgical. Remove parts of the mirror edge in a pattern, not randomly, strategically. You remove regions where the arrows would cancel and keep regions where the arrows would align. You manipulate which paths survive the sum. And suddenly, an area of glass that should not reflect begins to reflect strongly in a specific direction. You have created reflection by removing material. That is what a diffraction grating is, a device that doesn't force light into one path, but filters the set of possible paths so the remaining arrows add instead of cancel. And it works so reliably you can buy it, use it, build technology on it. We split light into rainbows. We analyze starlight. We measure atomic fingerprints. We do spectroscopy, the art of learning what something is made of by how it interacts with light, because diffraction gratings and interference patterns are stable, repeatable consequences of path summing. Now here's the uncomfortable implication. Those unseen paths weren't imaginary in the casual sense. They were present in the computation. Their cancellation was part of why the normal world looks normal. When you change the geometry, you change the cancellation and you reveal what was hidden. So the path picture is not just a cute philosophy. It's a machine that predicts real optical behavior. And this is not just about light. Electrons do it too. Everything does it. You can take an electron, fire it at a barrier with two slits, and ask a simple question. Which slit did it go through? Your intuition says one or the other. Nature says both, not half through each. The whole electron through both, because you must add the arrows for both histories, and the interference pattern you observe is the signature of a particle interfering with itself. One particle, multiple paths, one result, and the only way to make sense of the result is to accept the rule: add all possible histories. The two-slit experiment is the cleanest punch to common sense. If electrons were tiny bullets, you would see two piles on the screen behind the slits, one pile for each hole. But you don't. You see stripes. Bright, dark, bright, dark. An interference pattern. So you say, fine, maybe the electrons are colliding with each other like waves do. Then you make the experiment crueler. You send them one at a time. One electron, wait, record the hit. Another electron, wait, record the hit. And the stripes still appear, slowly building up dot by dot. That means the electron is not interfering with other electrons. It is interfering with itself, which means you cannot say it went through slit A or slit B in the ordinary sense. The observed pattern requires that both paths contributed to the final probability. Now you might think, okay, maybe this is special to space, maybe it's just geometry. But the path-summing rule doesn't stop at space. When you write it in full generality, you must sum over histories in space-time, and that introduces a strange feature: paths that go backward in time. Now, taken literally, backward in time sounds like science fiction, but in the mathematics of quantum field theory, contributions that look like particles traveling backward in time show up naturally, and if you exclude them, you get the wrong answers, so you include them. And then something remarkable happens. Those backward in time contributions can be reinterpreted as something moving forward in time with opposite charge. A positron, antimatter. In this view, antimatter is not a separate fantasy substance. It is what certain space-time paths look like when you translate them into the forward time story your brain can handle. And the reason physicists take this seriously is not because it's a poetic idea. It's because it works. When you include all the relevant histories, forward, backward, ordinary, weird, and you add the arrows correctly, you can compute quantities like the electron's magnetic behavior with outrageous precision. We are talking agreement between theory and experiment to around 12 decimal places in some cases. That level of accuracy is not a coincidence. It's not a vibe. It's a fingerprint of a correct underlying rule. So we face an uncomfortable truth. Reality behaves as if every allowed history contributes. And what you observe is what survives after interference cancels most of the possibilities. Now the mind immediately reaches for the biggest question. If all possibilities contribute, why do we experience only one outcome? How does the universe go from a cloud of amplitudes to a single click on a detector, a single dot on a screen, a single event? And here is the only honest answer. We don't fully know. We know how to calculate. We know the rules. We know they match experiments better than anything else humanity has ever built. But what it means, what is happening underneath the calculation, what exploring truly is, that remains one of the deepest open mysteries in physics. The math tells you what to do. It does not tell you what the world is really doing while you do it. Now let's take the path picture and watch it explain something that looks like a totally different law: the uncertainty principle. People often treat uncertainty as a mysterious extra rule glued onto quantum mechanics. But in the path language, it falls out naturally. Imagine forcing a particle to be in a very small region. That is what measuring position precisely means. It's like forcing the particle through a narrow slit. You are saying, it must be here, not there. But we already know what narrow slits do. When you squeeze the slit, the particle spreads out after it passes through. The outgoing directions become wide. The momentum becomes uncertain, not because nature is punishing you, because when you restrict the allowed paths, you destroy the neighborhood of nearly identical paths that would have reinforced a clean, straight outcome. The straight path loses its supporting crowd. Other angled paths survive. The distribution widens. Uncertainty is what happens when you remove paths, and the same logic explains lenses. A lens is thick in the middle and thin at the edges. Light traveling through glass is slowed compared to light traveling through air. So a lens can be shaped so that paths that would normally take different times are adjusted to take nearly the same time. The middle path goes through more glass and gets delayed. The edge path goes through less glass and gets delayed less. Done correctly, many paths arrive with phases aligned, arrows pointing the same way. The cancellations disappear, the arrows add, and you get a focus, a bright point where all those histories reinforce rather than erase one another. So with one rule, sum over paths, you get straight-line optics, diffraction, focusing, interference, and uncertainty as different faces of the same underlying arithmetic. And then you arrive at the final, disturbing implication. This isn't just about photons and electrons. Everything is made of photons and electrons, which means the solid, ordinary world you trust is built from entities that behave as if they are exploring a vast ocean of possibilities at every moment. Most of those possibilities cancel. So you see a stable chair, a stable wall, a stable body. But the stability is not the absence of alternatives. It is the result of interference selecting what remains visible. And when you change the conditions, when you carve a grating, close a slit, add a detector, you change the interference and the world responds. So the path picture gives you a brutal kind of wonder. Reality is not a single story. It is a sum of stories. And the one story you experience is what survives the cancellation. How the universe turns that sum into a single experienced outcome, why we see one result rather than all of them at once, is still not settled. But the rule that forces us to ask the question is settled. Add all possible histories. Square the amplitude to get a probability. And prepare to live in a universe that refuses to fit inside common sense. Because common sense was built for rocks and weather, not for a world where the straight line is not chosen, only selected by cancellation.